Usually, when we talk about writing code or, programming a computer, there's
Mhm.
this underlying expectation of just absolute unbroken precision.
Right, yeah. It feels very binary.
Exactly, it's binary.
Yeah.
You type a command into your terminal, say, print hello, and the screen just instantly, flawlessly outputs the text.
You change a variable from a 0 to a 1, and a logic gate deep inside the processor flips.
Yeah, and the environment is entirely synthetic, which means it's clean.
Yeah.
It's completely predictable.
And we find a tremendous amount of comfort in that absolute certainty. I mean, a software environment is a completely self-contained, perfect digital universe. The laws of physics just, well, they don't apply unless we explicitly program them to.
But the moment you take that perfect digital code and try to use it to control a physical machine, that illusion of absolute control just shatters completely.
Oh, absolutely. You step out of that sterile software environment and into the world of robotics or, industrial automation or drone flight.
Right. You write a line of code telling a heavy robotic arm to swing exactly 90 degrees, but it doesn't just snap to 90 degrees.
No, of course not. The momentum carries it to 95 degrees.
Yeah. So the motor yanks it back, and it bounces to 87 degrees, and then it just vibrates wildly before finally eventually stopping.
Because you have officially collided with the messy, chaotic reality of the physical world. I mean, friction, gravity, inertia, electrical resistance. None of these things care about your perfect line of code.
They really don't.
It's what engineers often refer to as the muddy waters of control systems. And bridging that gap between perfect digital intent and imperfect physical reality is, well, it's arguably the most important problem in modern engineering.
Which brings us to the mission for today's deep dive.
Hmm.
We are going to unpack the algorithm that single-handedly bridges that gap.
It is one of the most important yet profoundly misunderstood concepts in all of engineering, the PID controller.
Yeah. Our goal today is to break this down so clearly that a 15-year-old who is just getting into building their first Arduino robot, or honestly, just anyone listening right now who is insanely curious about how machines interact with the real world can completely grasp it, from the conceptual philosophy all the way down to the heavy mathematics.
It's a massive topic, and to do it justice, we are pulling from a really diverse, incredibly dense stack of sources today.
A huge stack.
Yeah, we're looking at university lectures from Matthew Peat, as well as a control systems curriculum from Rohini College.
Yeah.
We have technical manuals and software documentation from MapleSoft and MathWorks.
Right.
And we're also heavily referencing the foundational textbook by Carl Johan Aastrom and Tor Hegland, which is essentially the Bible of advanced PID control.
And maybe my favorite piece of the stack, we are leaning on a brilliant, highly accessible engineering paper by Tim Westcott titled PID Without a PhD.
Such a great paper.
It is. Because, let's be honest, the acronym PID, which stands for Proportional Integral Derivative, it sounds like terrifying, impenetrable calculus.
It sounds like a subject designed entirely to weed out engineering undergrads.
Exactly. But Westcott's paper is a classic, specifically because it cuts through that intimidation factor.
Right. The math is absolutely there, and we are going to get into it, but the equations are really just expressions of a much deeper philosophy.
The acronym PID is actually just a formalized way of teaching rigid, unthinking machines to gracefully interact with a chaotic, unpredictable environment.
It's the secret digital brain of the modern world. I mean, when you see a quadcopter drone hovering perfectly still in a gusting windstorm, that is a PID controller making thousands of micro adjustments a second.
Wow. Yeah. Or when you set your car's cruise control to 65 miles per hour, and the car maintains that exact speed even as you crest a steep hill and start rolling down the other side.
That is a PID controller manipulating the throttle.
So let's start at the very beginning. Let's build a conceptual model of what this algorithm actually is before we look at a single equation.
A conceptual foundation is critical, because before you can understand a PID controller, you have to understand the basic concept of a closed-loop feedback system.
Okay, let's unpack this. Imagine you are building a robotic arm. Let's say its only job on an assembly line is to lift a heavy steel box from the floor to a shelf at an exact specific height, say exactly 10 feet in the air.
A classic industrial automation problem. And it introduces our three foundational terms. In the language of control theory, that exact 10-foot height we want the box to reach is called the set point, or the SP.
The SP. That is the dream. That is the perfect digital intent.
Right. but the arm is currently sitting on the floor.
Exactly.
So the actual real-time height of the box at any given millisecond is called the process variable, or the PV.
Okay, so the process variable is reality.
Yes. So if the box is on the floor, the PV is 0. If the box is halfway up, the PV is 5 feet.
Which means we have a gap between the dream and reality.
We do. And that gap is our third term, the error. Mathematically, error is simply the set point minus the process variable.
Okay, simple enough.
And the entire job of the PID controller, I mean, its sole reason for existing, is to continuously look at that error and decide how much electrical current to send to the robotic arms motor to force that error down to absolutely 0.
That brings us to the first letter in our acronym, the P, proportional control. From a pure common sense standpoint, how does the machine decide how hard to pull?
Well, proportional control is essentially the machine's primary reflex. It's the most intuitive way to control anything. The fundamental rule of the P term is straightforward. The output of the controller, meaning how much voltage it sends to the motor, is directly proportional to the size of the error.
So the bigger the error, the bigger the response.
Exactly. If the error is massive, the response is massive.
So if our box is sitting on the floor at 0 feet and our set point is 10 feet, we have an error of 10. The controller sees that huge number and says, give the motor maximum power, and it yanks the heavy box upward.
Correct. The controller multiplies the error by a specific number called the proportional gain, usually written as KP.
KP8.
If your KP is set to 2 and your error is 10, the controller outputs a value of 20 to the motor drive. But consider what happens next. A fraction of a second later, the box has been lifted 3 feet into the air.
Now, the process variable is 3, but our set point is still 10, so our error has shrunk from 10 down to 7.
Right. And because the error has shrunk, the proportional output shrinks as well. 7 times our gain of 2 is 14, so the controller tells the motor to pull a little bit less violently.
It's exactly like driving a car on the highway.
Yeah.
I mean, if the speed limit, your set point is 65 miles per hour, and you are merging onto the highway going 20 miles per hour, your error is huge. You mash the gas pedal to the floor.
You give it everything.
Right, but as your speed climbs, as you hit 40, then 50, then 60 miles per hour, your error is shrinking. So your foot naturally, organically eases up on the gas pedal. The closer you get to the target, the less force you apply.
It's an excellent mental model. And as our sources, particularly the introductory materials from MathWorks, point out, this graduated proportional response is vastly superior to a simple on-off switch. Well, think about a cheap space heater. It just blasts 100% heat until the room hits 70 degrees and then it shuts off completely.
Right.
But the remaining heat in the coils radiates out, pushing the room to 74 degrees. Then it cools down to 68 degrees and the heater blasts back on at 100%. It's a constant, uncomfortable cycle of extremes. Proportional control gives you a nuanced, graceful approach curve.
So, if proportional control gives us this nice, smooth approach, why don't we just stop there? Why do we need the I and the D?
Because proportional control, when used entirely by itself on a physical machine, has a fatal flaw.
Fatal flaw?
Yes, it fundamentally guarantees failure in systems dealing with constant opposing forces. It creates a phenomenon called steady-state error.
Steady-state error.
Let's look back at your robotic arm lifting the heavy steel box.
Okay, the arm is lifting the box closer and closer to the 10-foot shelf. The error is getting smaller and smaller.
And because the error is shrinking, the proportional controller is telling the motor to pull with progressively less and less electrical force. But remember, that steel box is incredibly heavy. Gravity is a constant, unrelenting downward force. It never eases up.
Oh, I see where this is going. The motor is getting weaker as it approaches the shelf, but gravity is staying exactly the same.
Exactly. Eventually, the arm reaches a specific point. Let's say it's hovering at 9 feet 8 inches. It is just 4 inches below the target shelf.
Almost there.
Right. But at that exact height, the error is so small that the proportional push from the motor exactly perfectly equals the constant downward pull of gravity. The upward force and the downward force cancel each other out. The system reaches a state of perfect physical equilibrium.
So the arm just stops moving. It stalls out completely 4 inches below the target.
It permanently stalls. Think about the logic of the math here. If the arm somehow moved an inch closer to the shelf, the error would shrink even more. The motor's upward force would drop below the force of gravity, and gravity would immediately pull the box back down to that equilibrium point.
Wow.
A pure proportional controller requires an error to exist in order to generate any output at all. If the error reaches 0, the motor output reaches zero. And if the motor output is zero, gravity drops the box.
Right.
Therefore, when fighting a constant disturbance like gravity or a steady heat leak in a furnace, a P-only controller will never, ever hit the set point. That permanent maddening gap is the steady state error.
That would be incredibly frustrating to watch as an engineer. I mean, you've written this elegant code, the robot moves swiftly, and then it just stubbornly hovers a few inches away from success forever.
Very frustrating.
So if I'm the engineer in this scenario, my first instinct is just to crank up that proportional gain number we talked about. If the motor is too weak at the end, just make KP massive. Make it so even a tiny 4-inch error results in a huge surge of motor power. Does that fix it?
It seems like the logical solution, but it actually introduces a much more dangerous physical problem. Instability.
Instability.
Yes. If you crank that proportional gain incredibly high, yes, a tiny error will cause a massive motor response. But let's say a gust of wind slightly bumps the robotic arm. The sensor registers a 1-inch error. Because your gain is so massive, the controller panics and sends a violent surge of maximum power to the motor to correct that tiny bump.
Ooh, so the arm violently jerks upwards.
It jerks upwards so fast that the momentum carries it right past the 10-foot shelf. Now the box is at 10 feet, 2 inches. The error is negative. The massive gain kicks in again, violently reversing the motor. The arm slams downward, overshooting again.
Yep.
Very bad. By just cranking up the P term, you haven't solved the steady-state error. You've turned your expensive robotic arm into a chaotic, violently oscillating metronome that is going to tear its own gears apart.
Okay, so we cannot just use brute force. We need a smarter way to eliminate that stubborn 4-inch gap without making the whole system unstable. And that brings us to the second letter of our acronym, the I, the integral term.
Right.
I like to conceptualize the integral term as the machine's memory. It's the controller's sense of history.
That is the perfect way to visualize it. If the proportional term lives entirely in the present moment, only looking at the gap as it exists right now, the integral term is constantly looking at the past.
Okay.
Mathematically, an integral is an accumulation. It is the continuous sum of a value over time.
So how does that apply to our 4-inch steady-state error?
Well, the I term in our software loop is constantly watching the error and running a tally. It adds up the error, millisecond by millisecond. When our robotic arm stalls out at 9 feet, 8 inches, the proportional term is essentially helpless. It's stuck. But the integral term notices. It says, we have an error of 4 inches. A second goes by, we still have an error of 4 inches. 2 seconds go by, still 4 inches.
It's like a really stubborn friend who remembers every single little slight. Like if you are 5 minutes late to lunch, it's not a big deal. But if you're 5 minutes late every single day for a year, that friend is keeping a mental ledger.
Yes.
They're adding up all those tiny 5-minute delays until the sum total becomes a massive grievance and they finally snap.
That is exactly the mechanism. The integral term takes that tiny, seemingly insignificant 4-inch physical gap, and by integrating it over time, allows it to grow into a massive mathematical value inside the code.
Wow.
As that accumulated mathematical sum grows larger and larger, the I term commands the motor to push harder and harder and harder.
So even though the physical position of the box hasn't changed, the motor is slowly ramping up its power.
Precisely. The I term acts as an ever-increasing booster rocket. Eventually, it adds enough extra electrical juice to the motor to finally overcome the steady pull of gravity. The arm slowly pushes that box the final 4 inches, placing it perfectly on the 10-foot shelf.
Success.
Yes. And once the error hits absolute zero, the integral term stops growing. It holds its accumulated value, providing the exact, continuous amount of extra power needed to perfectly counter gravity forever.
That's brilliant.
As Matthew Pete's lecture materials emphasize, the primary fundamental mathematical purpose of integral control is the complete elimination of steady-state error. It guarantees you will cross the finish line.
So, proportional gets us moving fast. Integral ensures we actually hit the exact target without permanently stalling. This sounds like a complete functioning system, a PI controller. Why do we need to complicate things further with the D? What is the derivative term doing?
Well, to understand why we need the D term, we have to look at the physical consequence of combining proportional and integral control on a heavy machine. Let's go back to the moment the integral term finally ramps up enough power to overcome gravity and pushes the box those final 4 inches.
Okay, the box is moving up. It hits 10 feet. The error is 0. We win.
We do hit zero error, but look at the state of the system at that exact moment. The integral term has been building up this massive reservoir of mathematical energy to fight gravity. The moment the box hits 10 feet, the proportional term shuts off because the error is zero. But the integral term is still holding all that accumulated past history.
Oh, wow. So even though we are at the target, the motor doesn't instantly realize it's time to stop.
Right. It takes time for the error to become negative and for the integral term to start slowly unwinding its massive sum. But the physical world doesn't wait for the math to unwind.
No, the robotic arm is heavy. It has momentum.
Exactly. The lingering power from the I term, combined with the physical inertia of the moving arm, means the box blasts right past the 10-foot shelf. It overshoots.
And once it overshoots, the error is negative. The arm is too high, so the controller suddenly realizes it went too far, panics, and reverses the motor to pull it back down.
But then it might overshoot on the way back down too, because both the P term and the I term are fundamentally reactive. They only respond to an error that already exists.
Nice.
In physical systems with a lot of mass or a lot of thermal inertia, reacting only to the present and the past guarantees that you will constantly be a step behind the physical reality. You end up with the robotic arm bouncing up and down around the shelf.
Oscillating. Which, if we are talking about an industrial robot holding a heavy steel box or a surgical robot holding a scalpel, is a catastrophic failure.
It is entirely unacceptable. We need a way to look into the future. We need a way to anticipate the overshoot before it happens, and that is the D, the derivative term.
So if the P is the present and the I is the past, the D is the fortune teller.
Yes. A derivative, in pure calculus, is a measurement of the rate of change. The D term does not care at all about the size of the error. It doesn't care if the box is 100 feet away or 1 inch away. It only cares about how fast that error is shrinking or growing.
Okay, let's bring back our driving analogy. Let's say I'm driving that car, and my target is a red stop sign. If I am 50 feet away from the stop sign, my proportional error is small. But if I am 50 feet away and I am still traveling at 60 miles per hour, my brain realizes something terrifying.
Your brain calculates the rate of closure. You see that the error is shrinking incredibly rapidly.
Exactly. Even though I haven't reached the stop sign yet, I know an overshoot, a crash is imminent. So what do? I don't wait to cross the line before I react. I slam on the brakes early. I intentionally fight against my forward momentum to ensure I come to a smooth, complete stop exactly at the line.
That is a brilliant visualization of the derivative term. The D term acts as synthetic mathematical friction. Or another way to think of it is as a predictive shock absorber.
A shock absorber. I like that.
If the robotic arm is rocketing toward the shelf too quickly, the D term sees that steep rate of change. It calculates that if this velocity continues, an overshoot is mathematically guaranteed. So the D term actually generates a negative output. It subtracts power from the motor.
It actively fights against the other terms.
Yes. It fights against the proportional and integral terms, hitting the brakes to slow the whole operation down and ensure a soft, perfect landing right on the set point.
This conceptual framework is beautiful. Proportional is the immediate muscle reacting to the present gap. Integral is the memory, ensuring we don't succumb to long-term failure or steady-state error. And derivative is the intuition, anticipating the future and hitting the brakes so we don't crash. It is an incredibly elegant trinity of control.
It really is. When properly balanced, a PID controller can make a lumbering, 1,000-pound industrial robot move with the grace and precision of a ballet dancer.
But as much as I love our analogies, we have to acknowledge that we are talking about engineering. And engineers cannot just sit at a computer terminal and type, act like a stubborn friend, or hit the brakes like you see a stop sign.
No, they certainly cannot.
They have to translate these conceptual philosophies into hard, rigorous mathematics. Which brings us to the bridge between the physical and the digital. How do we actually model this?
This is where we transition from physical intuition to mathematical rigor. Before an engineer can write a single line of effective PID code, they have to deeply mathematically understand the physical machine they are trying to control. They need a mathematical model of what control engineers call the plant.
Okay, just to clarify the terminology for our 15-year-old listener, the plant is just the generic engineering term for the physical thing being controlled, right? The robotic arm, the quadcopter drone, the industrial furnace.
Correct. The plant is the physical hardware, and the mathematical tool we use to model the behavior of that hardware is called a transfer function.
A transfer function. Now, I am looking at the curriculum notes from the Rohini College source material, and they offer a very specific, very intimidating definition.
Oh boy, let's hear it.
It says a transfer function is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input, assuming zero initial conditions. Let's stop right there. Laplace transforms. Assuming zero initial conditions, we promise to keep this accessible, and suddenly we are dropping advanced differential calculus terms.
It sounds deeply intimidating, I know. But if we break down why we need it, the concept is actually a brilliant, labor-saving shortcut.
A shortcut.
Yes. Let's think about what a physical robotic arm actually is. It is a mass of metal. It is being moved against the force of gravity. Its joints experience mechanical friction. The motor relies on electrical current generating magnetic torque.
Right. It's a complex stew of interacting physical forces.
Exactly. And all of those forces are constantly changing over time. If you want to describe that physical system mathematically, using normal time-based math, you have to use differential equations. You have to write equations that track the rate of change of the current, the rate of change of the velocity, the rate of change of the position, all simultaneously.
That's so awful.
Differential equations are agonizingly messy. They are incredibly difficult to solve and even harder to use for designing a software controller.
So we need a way out of the time domain. We need a way to escape the mess of differential equations.
Which is exactly what the Laplace transform does. The Laplace transform is a mathematical operation that takes those messy, time-based differential equations and literally transports them into a completely different mathematical dimension. Control engineers call this alternate dimension the S domain, or the complex frequency domain.
So wait, we take a physical robot, turn it into a calculus equation, and then magically wave a Laplace wand to turn it into something else. What makes the S domain so much better?
What makes it magical is that in the S domain, complex calculus operations literally devolve into simple algebra.
Really? Just algebra?
Just algebra. Differentiation, calculating the rate of change, simply becomes multiplying by the variable s. Integration, calculating the accumulated sum, simply becomes dividing by s. You trade the nightmare of solving differential equations for the absolute simplicity of basic algebraic addition, subtraction, multiplication, and division.
It is a translation device. It is like taking a highly technical novel written in a language you don't understand, running it through a perfect translator into your native language, easily editing the text, and then translating it back to the original language.
That is an excellent analogy. A transfer function is quite literally just an algebraic fraction in the S domain. It is the output divided by the input. If I put 10 volts of electrical input into the motor, the transfer function algebraically calculates exactly how many degrees of output movement the arm will produce.
And what about that zero initial conditions part?
Oh, the Rohini College definition mentions assuming zero initial conditions simply because it makes the math cleaner. We assume the robot is resting at zero before we start the calculation, so we don't have to carry over lingering mathematical baggage from whatever the robot was doing 5 minutes ago.
Okay, I am tracking with you. The transfer function is an algebraic shortcut to understanding the physical plant. So once the engineer has this magical fraction, this equation filled with the variable s, what are they actually looking for? How does it help them build the PID?
They look at the denominator of that algebraic fraction.
Yeah.
Specifically, they look for the highest exponent, the highest power attached to the variable s. That single number tells the engineer the fundamental order of the system.
The order. Like a first-order system or a second-order system, what does that actually mean in the real physical world?
In a working physical interpretation, the order of the system tells you exactly how many dynamic, energy-storing elements exist within the hardware.
Energy-storing elements.
Yeah. How many physical components can hold onto energy and release it later? Is there a massive weight holding kinetic energy? Is there a tight spring holding potential mechanical energy? Is there a large capacitor holding an electrical charge? The higher the order, the more energy-storing elements there are, the more complex, sluggish, and potentially unstable the physical system is.
Which brings us to analyzing the simplest version, the first-order control system. Following your logic, if we look at our transfer function, and the maximum power of s in the denominator is just one, literally just s to the power of what we have a first-order system.
Correct. The classic mathematical form for a first-order system usually looks something like k divided by the quantity t times s plus 1. In that equation, t is the time constant, which tells us how fast the physical system naturally responds to a change, and k is the DC gain, which tells us the final scale of the output.
Let's pull that out of the math and into reality. What does a first-order system look like?
First-order systems are generally simple, somewhat sluggish systems that fundamentally do not have the physical capacity to bounce or oscillate on their own. They only have one energy-storing element.
Can you give me an example?
A perfect example is a basic electric heater controlling the temperature of a room, or the speed control of a very simple, heavily loaded electric motor. Energy only goes in, and it slowly bleeds out. There are no opposing energy storage mechanisms fighting each other. A room doesn't naturally rapidly bounce between 50 degrees and 90 degrees on its own.
Right. So if I am an engineer and I have modeled my physical plant and discovered it is a first-order system, what is my PID strategy?
It is relatively straightforward. As
Okay.
the math works in MapleSoft curriculum materials detail, if you apply pure proportional or P control to a first-order system, the combined system fundamentally remains a first-order system. It stays mathematically simple.
Okay, good.
It will never suddenly develop the ability to bounce or go crazy. However, as we discussed with our gravity analogy, it will always suffer from steady-state error. If you command that first-order room heater to reach 72 degrees using only P control, it will constantly lose heat through the walls, reach an equilibrium, and permanently stall out at, say, 70 degrees.
Heat is constantly escaping,
Yeah.
creating that unclosable gap. So we know the solution to this. We bring in our stubborn friend. We add the integral term to accumulate that 2-degree error over time and force the heater to reach exactly 72 degrees.
Yes. You add integral control, creating a PI controller. The steady-state error is eliminated. From a performance standpoint, problem solved. But from a mathematical and physical standpoint, a fascinating transformation has just occurred.
What kind of transformation?
Think about the math of the Laplace domain we just discussed. Adding an integral term means you are mathematically dividing by s. When you combine the transfer function of the PI controller with the transfer function of your first-order plant, you have to multiply them together. You introduce another s into the denominator. So your s to the first power system becomes an s-squared system. By simply adding a line of code to remember past errors, you have fundamentally changed the dynamic nature of the entire system.
Wait, really? Just by giving the digital controller a memory, the physical system behaves as if it suddenly grew a new physical property.
Exactly. The MapleSoft source material explicitly highlights this exact phenomenon. A simple, sluggish, first-order plant, when controlled by a PI controller, dynamically behaves like a second-order system.
Wow.
It suddenly gains the potential to overshoot the target temperature and oscillate, a physical behavior and never possessed before you added that specific software. It is a profound illustration of how deeply and inextricably the digital code and the physical hardware become intertwined in closed-loop control. You are literally rewriting the physics of the machine with mathematics.
That is incredible, and that leads us to deeply examine those squared systems. The second-order control system. Now, the highest power in our denominator is squared. We have leveled up in complexity.
We have. And this is where the vast majority of challenging robotics, aerospace, and industrial automation work lives. Second-order systems inherently possess two energy-storing elements.
Two of them.
Yes. The classic physics textbook example is a heavy mass hanging on a flexible spring. The mass stores kinetic energy as it moves up and down, and the spring stores potential energy as it compresses and stretches. They constantly trade that energy back and forth.
Which means bouncing, shaking,
Right.
vibration.
Precisely. And mathematically, a second-order transfer function is defined by two absolutely critical physical variables. The first is the undamped natural frequency, denoted by the Greek letter omega sub n.
Omega sub n, got it.
This is the baseline frequency at which the physical system wants to shake or vibrate if you just hit it with a hammer and let it ring in a vacuum.
Like striking a metal tuning fork. It is a natural inherent pitch it wants to sing at.
Exactly. The second variable is the damping ratio, denoted by the Greek letter zeta. This represents the system's internal physical resistance to change. How much friction, drag, or air resistance is naturally built into the physical hardware to absorb that energy and stop that ringing.
Okay, let me test my understanding here. If I take that mass on a spring and I submerge the entire thing in a vat of thick, heavy molasses, the damping ratio zeta is very high. It's not going to bounce much at all. It will just slowly ooze back to its resting position.
Exactly.
But if I put that exact same mass and spring in a vacuum chamber, zeta is incredibly low. It'll bounce for a very long time.
That is a perfect physical understanding. And here is where the Laplace mathematics reveals the absolute truth of the reality. If you solve the roots of that squared denominator, what engineers call finding the poles of the system, the value of that damping ratio, zeta, determines everything.
How so?
If zeta is greater than 1, the system is overdamped, like your molasses vat. But if zeta is less than 1, the mathematical poles suddenly become complex numbers. They gain an imaginary component.
Imaginary numbers, like the square root of -1. I thought we were dealing with physical reality.
We are. And in control theory, An imaginary mathematical pole has a profoundly real physical consequence. It mathematically guarantees that the system will physically oscillate, it will bounce, it will vibrate.
Oh, wow.
Think of a car driving over a deep pothole. If the shock absorbers, the dampers, are completely blown out, the car's heavy chassis acts like a mass on the suspension springs. The damping ratio drops below 1, the mathematical poles become imaginary, and the physical car just keeps violently bouncing down the road long after the pothole is gone.
And obviously, if you are engineering a multi-million-dollar surgical robotic arm or a drone carrying a heavy camera near a building, having a system that naturally wants to bounce and vibrate is incredibly dangerous.
It is a recipe for disaster, so engineers have to figure out how to control these second-order systems meticulously. And what tool from our PID acronym do they rely on most heavily here?
This is where the derivative term puts on its cape.
Yeah.
It's the superhero of the second-order system.
It absolutely is. With a highly oscillatory second-order system, engineers rely extensively on PD proportional derivative control, or full PID control. If the natural physical system doesn't have enough friction, if the hardware's natural zeta is too low, the derivative term steps in to act as that synthetic friction we discussed earlier.
It's just a brilliant engineering solution. If you build a robotic arm and it bounces too much, you don't have to tear the whole machine apart, rebuild the joints, and physically pack them with thick, heavy grease to add mechanical friction. You just add a D term to the software loop. The code simulates the physical molasses. It calculates the rate of change, anticipates the bounce, and electrically brakes the motor against it.
Exactly. Matthew Pete's lecture materials note that for a second-order system, manipulating the gains of a PD controller allows engineers to essentially place those mathematical poles anywhere they want on the complex plane.
They can just move them around.
They can take a highly unstable, bouncy physical machine, and by carefully tuning the P and D numbers, force it to behave as if it were perfectly damped. They literally rewrite the dynamic physics of the machine using a digital algorithm.
That is deeply fascinating. We have essentially conquered physics with math. But, and I know from experience, there is always a but. When discussing engineering, the math we are talking about here assumes a perfect universe.
It really does.
The equations assume that our sensors are completely flawless, that our wires have zero resistance, and that our motors possess infinite, unlimited power. What actually happens when these pristine equations are forced to interact with cheap physical hardware?
Things go wrong. Things go very, very wrong. When the infinite demands of mathematics collide with the finite limits of physical hardware, you encounter a whole new tier of engineering nightmares. And perhaps the most notorious destructive disaster in PID control is a phenomenon known as integrator windup.
Okay, let's explore this. Set the scene for me. How does windup actually happen?
It all stems from a physical reality called actuator saturation. The pure mathematics of a PID controller assume that the actuator, the motor, the fluid valve, the heating element, can always perfectly deliver whatever amount of power the equation demands.
Right.
If the PID math calculates a massive error and asks for 150% power, the math simply assumes 150% power will be delivered. But in the real world, a valve can only physically open 100%. An electric motor can only spin so fast before it reaches its maximum voltage limit. It hits a physical wall, it saturates.
Right. It goes back to the car analogy. If I am merging onto the highway and I push the gas pedal all the way through the floorboards, the engine gives me everything it has. It gives me 100%. But if the abstract math in my head says we need even more acceleration to merge safely, pushing the pedal harder into the carpet isn't going to make the physical car go any faster.
Precisely. Now let's map that onto an industrial scenario. Imagine your heavy robotic arm is asked to move a massive steel box over a very long distance very quickly. The set point changes drastically.
Huge error.
The proportional term suddenly sees a colossal error. It runs the math and instantly demands, say, 250% motor power to close that gap quickly. But the physical motor controller maxes out at 100%.
Okay, so the robotic arm is moving toward the target as fast as it physically can, but it is not moving as fast as the math wants it to move.
Exactly. And because the physical arm is moving slower than mathematically expected, the error is not shrinking as fast as it should. And who is watching that persisting error?
Our stubborn friend. The integral term.
Yes. The integral term sees that this massive error is persisting longer than it mathematically should. So it starts doing its job, it starts accumulating, it sums up that massive error second by second, millisecond by millisecond. Because the arm is taking so long to cross the physical distance, the internal mathematical value of the I term grows into an absolutely colossal, completely unrealistic number. The integral term winds up.
It is stockpiling massive amounts of mathematical frustration. It thinks the robot is stuck, even though the robot is just moving as fast as it can. So when does this underlying math problem become a physical disaster?
The disaster triggers the moment the robotic arm finally gets close to the target shelf. As the arm approaches 10 feet, the current real-time error shrinks. The proportional term sees the small error and says, okay, we are close, ease off the motor power.
Makes sense.
But the integral term is still holding that massive, inflated, wound-up value of accumulated past errors. Even though the arm is practically touching the set point, the I term's internal mathematical sum is so huge that it is still screaming for 100% maximum power.
Oh no, so the motor stays pinned at absolute maximum velocity even as it physically crosses the target line.
Yes, it blasts right past the set point at full speed. It causes a massive, violent physical overshoot, and it gets worse.
How does it get worse?
Once it blasts past the target, the error becomes deeply negative. The arm is way too high. But before the controller can apply the brakes, the integral term has to slowly unwind that massive positive accumulated sum. It has to add enough negative errors to cancel out the huge positive number it built up.
Oh man.
While it is doing that math, the arm is still traveling in the wrong direction. By the time the I term unwinds enough to reverse the motor, the arm is wildly out of position. The system will violently oscillate, slamming back and forth with massive swings until the I term finally bleeds off all that excess phantom energy.
That's terrifying.
Tim Westcott's paper has a fantastic, terrifying visualization of this, showing a motor taking 3 to 4 times as long to settle purely because the software's internal output was pinned wildly outside the physical limits of the hardware drive.
That sounds like an incredibly efficient way to destroy a million-dollar piece of factory machinery. So if I'm the engineer, how do I fix this? How do I prevent the math from losing touch with reality?
Engineers use specific software algorithms broadly categorized as anti-windup mechanisms. The easiest, most computationally simple method, which Westcott points out, is simply clamping the integral state.
Clamping it.
You literally write a protective line of code that says, if the integral term's accumulated value exceeds the maximum physical output limit of a motor, stop adding to it. You just put a hard artificial ceiling and a hard floor on the memory.
That makes perfect logical sense. Don't let your stubborn friend remember a grudge that is larger than their physical capacity to act on it.
Exactly. It's crude, but effective. However, a much more sophisticated, elegant method is called back calculation. The textbook by Ostrom and Heglin, which is the gold standard for this, details this mechanism beautifully. In back calculation, the PID controller actually monitors its own physical limitations. It actively measures the actual physical output of the actuator and compares it to the theoretical output the PID math requested.
So it knows when it hits the wall.
Yes. If there is a difference, if the math asks for 150%, but the actuator is only delivering 100%, the controller realizes it is saturated. It takes that 50% difference and actively subtracts it back out of the integral term's accumulator, modified by a specific parameter called a tracking time constant. It dynamically, continuously forces the mathematical integral to reset itself, so it always perfectly matches the physical reality of the hardware.
It's almost like giving the software a sense of physical self-awareness. It realizes, my physical body cannot keep up with my mathematical brain. I better temper my expectations so I don't lose control later.
That is a profoundly accurate way to phrase it. That calculation keeps the math grounded in physical reality. Now, wind-up is the great danger of the integral term. But the derivative term has its own unique, terrifying, real-world nightmare, the noise problem.
I have heard this referred to as derivative kick. It's a great visceral name. What actually causes it?
Remember the fundamental nature of the derivative term. It is a mathematical differentiator. Its entire job is to look at the rate of change of the signal. In the pristine theoretical world of Laplace transforms and calculus, a signal is a perfectly smooth, continuous curve. But in the real world, the process variable signal comes from an electrical sensor, an optical encoder on a motor, or a thermocouple in a furnace.
And electrical sensors pick up noise.
Exactly.
Yeah.
Static electromagnetic interference from nearby power lines, tiny voltage ripples from the power supply.
So what we think is a smooth curve of the robot arm moving actually looks like a jagged, fuzzy, static-filled line if you zoom in close enough on an oscilloscope.
Exactly. Now, consider how the D term reacts to that fuzz. Imagine a tiny microscopic static crackle on your position sensor. It's just a tiny voltage blip lasting a microsecond. To the naked eye, the physical position of the arm barely changed. But the D term doesn't look at position. It looks at how fast the change happened. A static pop goes from 0 to its peak in a millionth of a second. To a pure mathematical differentiator, that tiny crackle looks like an instantaneous, incredibly massive spike in velocity. It looks like the physical robot arm just inexplicably accelerated to Mach 3.
Oh, wow. I see the problem. The D term relies on velocity to predict the future. So if it thinks the arm is suddenly moving at Mach 3, it panics.
It violently panics. It sees this massive false acceleration and instantly sends a chaotic maximum power brake signal to the motor to stop the perceived crash. But then, a microsecond later, the static noise spikes back down.
Oh, no.
The D term sees a massive deceleration and sends a massive accelerate signal. The pure derivative mathematically amplifies high-frequency noise to near infinity. If you were to hook a pure unfiltered derivative controller directly to a physical motor, the controller would send a rapid-fire machine gun blast of chaotic, full-power reversing signals. The motor would just violently vibrate in place, rapidly heat up, and quickly burn out its internal coils.
So wait, if the D term is supposed to be our synthetic friction superhero, but it instantly destroys the motor the second there's a tiny bit of electrical static, why use it at all? Why not just throw the D term out?
Because without it, our second-order systems will bounce out of control. We desperately need that predictive friction. So the engineering solution is that an engineer never, ever implements a pure derivative in the real world. They always modify the math to include a low-pass filter directly on the D term.
A filter. Like putting physical earmuffs on the controller so it can't hear the static.
Exactly like that. In the mathematical models, you'll often see this filter noted as a parameter n. The ideal pure derivative equation is modified. Instead of just differentiating, the signal is run through a mathematical low-pass filter.
What does the filter do?
What this filter does is act as a frequency gatekeeper. It allows low-frequency changes, the actual relatively slow physical movements of the heavy robotic arm, to pass through clearly to the differentiator. But it blocks or heavily dampens high-frequency changes like the microsecond pops of electrical static.
It muffles the high-speed static, so the D term only reacts to the slow, real movement of the heavy metal.
Precisely. And the control literature notes that typical, reliable values for that filter parameter n are usually somewhere between 8 and 20. It is a crucial, necessary compromise between pure math and physical reality. You intentionally limit the high-frequency gain, saving your hardware from vibrating itself to death, while still keeping enough of the predictive, stabilizing power of the D term to gently break the actual physical movements of the arm.
This is just incredible. The sheer amount of translation and compromise required between pristine mathematical theory and chaotic physical reality is staggering. You have to anticipate so many physical failures.
It's a lot of plates to keep spinning.
It really is. Which leads us perfectly into the practical application. I want to know from start to finish how a professional engineer actually builds one of these things. Walk me through the life cycle of implementing a PID controller in an actual industrial setting.
It is a highly rigorous, multi-step workflow. And crucially, it starts long before anyone touches a keyboard to write code. Step 1 is ideation and modeling.
So back to the physics textbook.
Absolutely. The engineer has to deeply understand the plant from fundamental first principles. If it is a chemical fluid tank, they have to map out the fluid dynamics, the pipe diameters, the viscosity. If it is an industrial motor, what is the exact rotor inertia? What is the mechanical damping constant of the bearings?
You really have to know the machine.
Yes. As the MapleSoft engineering source highlights, they literally write out the differential equations of all those physical forces, take the Laplace transforms we discussed, and build that foundational transfer function. You cannot possibly control a physical system safely if you do not mathematically know how it naturally behaves.
Makes total sense.
Yeah.
Know thy enemy. What is step 2?
Step 2 is digital implementation. It is important to contextualize that modern PIDs are very rarely built out of physical analog electronic circuits anymore, the way they were in the 1950s and 60s with op-amps and capacitors.
Oh, really?
Yeah, today, almost 100% of industrial PID controllers run completely digitally. They run as software algorithms on PLC's programmable logic controllers or embedded microprocessors like ARM chips.
So the complex calculus is just a software algorithm running in a loop.
Yes, but placing calculus into a computer introduces a profound new challenge. Think about pure calculus. It is inherently continuous. It flows smoothly through infinite slices of time. But digital computers do not experience continuous time.
Right, they operate in frames.
Exactly. They operate in discrete, choppy steps defined by a processor's clock cycle and a specific sampling period. They take a digital snapshot of the sensor, do some math, output a signal, wait a few milliseconds, and take another snapshot.
It's like watching a movie at 24 frames per second instead of seeing continuous real life.
Exactly. To translate continuous calculus into discrete, choppy computer code, engineers have to use mathematical approximations. For example, a computer cannot perform a true continuous derivative. So, to calculate the rate of change, a digital controller uses an algorithm like the backward difference.
How does the backward difference work?
It's incredibly simple arithmetic masquerading as calculus. Every time the computer takes a snapshot, say, every 10 milliseconds, it records the current error. To find the derivative, it simply takes that current error, subtracts the error from the previous snapshot 10 milliseconds ago, and divides by the elapsed time.
That's it.
That's it. It is a crude, choppy approximation of a smooth, continuous curve. But it works, provided the sampling rate of your computer processor is vastly, vastly faster than the physical movement of your mechanical machine. If the computer samples too slowly, the illusion of continuous control completely breaks down and the math fails.
Wow, okay. So we've modeled the intricate physics, we've carefully written the discrete digital code with anti-windup and noise filters. Step 3, the tuning phase. This massive equation running on a microchip. How do you actually pick the magic numbers? How do you choose the exact values for the proportional gain, the integral time, and the derivative time to make the robot arm move perfectly?
Tuning is where pure engineering science transitions into something resembling an art form. As the instructional materials from National Instruments and MathWorks detail, there are several accepted methods. The most visceral, and surprisingly the most common in the field, is the guess and check method, sometimes called manual tuning.
Guess and check. Really? For advanced industrial robotics? That sounds like a terrible idea.
It sounds unscientific, but it relies heavily on the engineer's deep physical intuition of the plant. The standard manual procedure goes like this. First, you set the integral and derivative gains completely to zero. You turn them off.
Okay.
You start with only pure proportional control. You command the robot to move, and you slowly, incrementally crank up the P gain. You watch the robot. You keep turning up the P gain until the system becomes unstable and starts to steadily, continuously oscillate without stopping.
You intentionally force the machine to bounce out of control.
Yes, you intentionally push it to the absolute edge of instability to find its physical limit. Once you find that limit, you back the P gain off by about half until the movement is stable but very fast. Now, because you only have P control, you will have that gap we talked about, the steady state error.
The robot stalls 4 inches from the shelf.
Exactly. So next, you slowly start dialing in the integral term. You increase it until it accumulates enough power to push the robot those last 4 inches and the steady state gap disappears. But remember the mathematical transformation we discussed earlier. Adding I introduces an S-squared dynamic. It introduces bounce.
Right. By fixing the stall, we've created a new problem. The robot is overshooting again.
Precisely. You have introduced overshoot. Finally, you bring in the superhero. You slowly increase the derivative term to apply that synthetic mathematical friction. You dial it up just enough to smooth out the integral bounce, dampening the overshoot and giving you a crisp, clean, perfect stop exactly on the set point.
It sounds exactly like tuning a guitar by ear. You pluck the string, turn the peg, listen for the wobble, and adjust until it sings true.
Yeah.
But what if the engineer doesn't have a good ear for robotics? What if they want a mathematically rigorous shortcut instead of just guessing?
There is a shortcut, and it is arguably the most famous tuning method in the history of control theory, developed back in the 1940s, the Ziegler-Nichols method. It is heavily featured in absolutely all of our source materials. It is a brilliant, standardized mathematical cheat sheet.
1940s. They were tuning PIDs before computers even existed.
They were. John Ziegler and Nathaniel Nichols were engineers at Taylor Instruments. They weren't using Python code or PLCs, they were using complex mechanical systems driven by compressed air flowing through pipes, pneumatic controllers.
Wow, pneumatic controllers.
Because tuning these pneumatic systems by trial and error was incredibly time-consuming and expensive for factories, they developed a rigorous, repeatable empirical method.
How does the Ziegler-Nichols method actually work?
It starts similarly to the manual method. You turn off the I&D terms, you use only proportional control, and you command the system to move. You increase the gain until the physical system oscillates with a constant, perfectly sustained amplitude.
Okay.
It's not dying out, and it's not wildly amplifying. It is holding a perfect, steady vibration right on the mathematical edge of flying out of control. That specific gain value that causes the sustained oscillation is recorded and called the ultimate gain, denoted mathematically as Ku.
The ultimate extreme limit of the physical hardware.
Right. And while the machine is physically oscillating at that ultimate limit, the engineer uses a stopwatch or an oscilloscope to measure the exact time it takes to complete one full bounce, one peak-to-peak vibration. That time measurement is recorded as the ultimate period, or TU.
So by just finding the edge of instability, you have discovered the absolute heartbeat and the power limit of the machine.
Exactly. You have characterized the physics of the plant using just two numbers. Once you have Ku and Tu, the difficult part is over. You literally just look at the empirical chart that Ziegler and Nichols published in 1942. The chart provides simple, standardized multipliers.
Give me an example. What does the chart say?
For a classic full PID controller, the Ziegler-Nichols chart tells you to set your proportional gain to exactly 0.6 times your ultimate gain. Your integral time becomes 0.5 times your ultimate period, and your derivative time becomes 0.125 times your ultimate period. You do that basic arithmetic, plug those three numbers into your digital controller, and almost instantly you have a very solid, highly functional baseline tune.
That is essentially magic. It is a paint-by-numbers recipe for complex calculus.
It is remarkably effective. But as all the experts, especially Ostrom and Hägglund, strongly warn, Ziegler-Nichols is merely a starting point. It is not the finish line.
Why not?
The original 1942 method was designed to reject disturbances quickly, which means it often yields a very aggressive tune. It will get to the target very fast, but it usually results in a significant overshoot, often around 25% before it settles. If that overshoot is unacceptable for your specific application, you have to move to the final step of the workflow, step 4, testing and refinement.
Time to see if the aggressive tune causes the robotic arm to smash through the wall.
Exactly. The engineer applies what is called a step response. They inject a sudden, drastic mathematical command to change position from 0 to 100% instantly. Then they watch the closed-loop physical system react. They monitor the response curve on an oscilloscope or in advanced software simulations like MATLAB Simulink.
What are they looking for on that curve?
They're looking at specific performance metrics. How fast is the rise time? How long does it take to first hit the target? How high is the maximum overshoot? Does it swing dangerously far past the goal? And what is the settling time? How many seconds does it take for the final microvibrations to stop entirely? Based on those metrics, they make tiny micro-adjustments to the PID numbers until the physical behavior perfectly meets the safety and speed specifications of the project.
And as Kim Westcott points out in his paper, there's a very real, very human psychological danger lurking in this final testing phase, isn't there?
There is a massive trap. He warns specifically against the endless tweak. Engineers, by nature, seek perfection. They can easily fall into a psychological trap where they just keep adjusting the numbers back and forth, endlessly chasing a mathematically perfect response curve that simply, fundamentally, does not exist within the physical limitations of that specific hardware.
At some point, you just have to step back and accept a good enough tune. And if good enough isn't meeting the factory speed or precision specifications,
then you must accept a hard engineering truth. You cannot fix it in software anymore. You have reached the limit of the algorithm. You have to go back to the drawing board and physically redesign the mechanical plant itself.
oh wow.
You have to buy a bigger motor with more torque, or design a stiffer robotic arm that doesn't flex, or buy a higher resolution sensor. Software can do incredible things, but it cannot infinitely compensate for inadequate physical hardware.
What a phenomenal journey this has been. We started with the basic, almost human logic of trying to figure out why a robotic arm wouldn't reach a shelf. We understood the immediate reflex of the P term, the lingering memory of the I term, and the fortune-telling anticipation of the D term.
We covered a lot of ground.
We really did. We took a terrifying but necessary plunge into the S domain with Laplace transforms to understand the actual math of dynamic first and second order systems. We navigated the real-world nightmares of actuator saturation and integrator windup and the noisy chaos of derivative kick. And we finally walked through the meticulous workflow of how a professional engineer actually models, codes, and tunes this digital brain using historical methods like Ziegler-Nichols.
It really highlights how profoundly interdisciplinary control engineering truly is. To be a great control engineer, you need the intuitive, tactile understanding of a mechanic, the rigorous analytical logic of a theoretical mathematician, and the structural discipline of a software programmer, all functioning simultaneously in your head.
For our listeners who have made it this far and want to go even deeper, because I know there are listeners out there who are already firing up their 3D printers and ordering Arduino boards right now, what are some advanced topics they should search for next to expand their understanding?
There is a vast, incredible world beyond basic, single-loop PID. I would highly recommend exploring 3 specific areas next. First, look into something called gain scheduling.
What does that entail?
Gain scheduling is where your PID parameters actually change dynamically depending on the current physical operating region of the machine. You might have one set of mathematically tuned PID numbers when a drone is hovering gently near the ground, and the software seamlessly swaps to a completely different, more aggressive set of PID numbers when the drone is flying at top speed through high winds.
Oh, that makes sense. It's like a car shifting gears to match the speed of the engine. What's the second area?
Second, explore feed-forward control. A standard PID controller is fundamentally purely reactive. It has to wait for an error to physically exist before it can calculate a solution to fix it. Feed-forward control attempts to anticipate known physics.
Anticipate it how?
If you are flying a drone and you know you are about to command a violent vertical acceleration, you don't wait for gravity to cause a massive error to build up. You instantly, simultaneously inject a massive spike of feed-forward baseline power directly to the motors at the exact moment you issue the command. You let the feed-forward handle the bulk of the known physics, and you let the PID feedback loop just quietly clean up the tiny, unpredictable remaining errors like wind gusts. It bypasses the fundamental delay of waiting for an error.
That is brilliant. Proactive physics instead of reactive calculus. And the third topic?
Cascade control. This is where you literally nest multiple PID loops inside of each other, operating at different speeds. For example, in a high-end CNC machine, you might have an outer, slower PID loop calculating the desired physical position of the cutting tool. That position controller feeds its mathematical output as a new set point to a faster inner PID loop that is controlling velocity.
Oh, wow. Loops inside loops.
Exactly. And that velocity loop feeds its output to a lightning-fast innermost hardware loop controlling the raw electrical current entering the motor coils. It allows for ultra-precise, incredibly stable automation by breaking down the physics into isolated layers.
Mind-blowing. Well, as we wrap up this massive deep dive, I want to leave you, the listener, with a final, somewhat philosophical thought to mull over. We have spent this entire time talking about complex industrial automation, about writing software to teach unthinking machines to mimic human-like reactions and anticipation.
Right.
But if you really step back from the equations and look at the fundamental logic structure of a PID controller, it is essentially humanity's attempt to mathematically replicate the biological nervous system.
It really is an astonishing parallel.
Think about your own body. When you accidentally touch a hot stove, your reflexes react violently to the immediate present pain to pull your hand away. This is pure proportional control.
Absolutely.
When you were learning to ride a bike, you learned from your past mistakes and lingering failures, slowly accumulating balance over time that is integral control. And when you are running through a dense forest, your eyes are constantly anticipating the future, tracking the rate of closure with trees, forcing your legs to adjust their stride before you hit an obstacle that is derivative control.
That's a perfect way to look at it.
As you walk around today, picking up a coffee cup, driving your car, or even just standing completely upright against the constant pull of gravity, think about the fact that your own brain is running a continuous, incredibly complex, perfectly tuned biological PID loop just to keep you from crashing into the messy physical world around you.
The complex calculus we put on silicon chips is just our way of mirroring the brilliance of biology.
Exactly. So the next time you see a robot awkwardly overshoot its target and vibrate for a second, maybe give it a little grace, it is just dealing with the exact same messy, chaotic physical reality we are, trying its best to translate a perfect digital intention into a profoundly imperfect physical world. Thank you so much for joining us on this deep dive. Keep asking questions, keep building, and we will see you next time.